Hello guys. Today we'll be reviewing and I'll be explaining topic B.4 in the IB Physics HL syllabus. So what is topic 4? Topic B.4 is an additional higher level subject, so it's only for HL students. It talks about thermodynamics and expands on the thermal laws you learned through from B.1 through B.3. So let's start with the most important law in thermodynamics. What is it? So I'm gonna write it down first as an equation and data booklet and I explain. So it says that the heat energy is equal to the change in the internal energy plus work done. So this law actually is known as the first law of thermodynamics, and it is simply the law of conservation of energy. Energy cannot be created nor destroyed, it can only be transformed from one form to another. And that's the case here. Let's let the change in internal energy be zero. That means that all heat energy uh, released is equal to the work done. If I do work on something, all of it will be converted to heat energy uh, if the internal energy of the object is zero, of course. This is probably the most fundamental law in physics, as it states that energy cannot be created nor destroyed, which is the case here, and we'll be using it a lot throughout this topic because it's easy to solve for any one of the three if you have the other two, or which I'll tell you later, but in some cycles or some reactions, uh, it is implied that one of them is equal to zero, so the other one is equal to one of the others, if you understand. So let's start with work here. The definition of work that you know is that work equals to force times displacement. So I wanted to derive the equation for work for gases here, and I'll show you how. So let's expand. Force is merely is kilogram, or let's say it's mass times acceleration times displacement. And more fundamental units, we could get mass times velocity times displacement over time, which is equal to mass times displacement squared, since velocity displacement over time over time squared. Okay. So the units here would be meter. Of course, for the mass it would be kilogram, then meter squared over second squared, which can be written in kilogram meter squared per second squared. Yes. Now let's see the one that is in the booklet. It states that work is equal to the pressure multiplied by the change in volume. So let's do the same here. Pressure is force over area, so we can do this area. And since we know that volume is in meters cubed and area is in meters squared, we can just say that it is equal to force multiplied by displacement. And here we see that it is the exact same as the equation for work in normal mechanics. Thus we prove they are actually in fact equal. So what does this equation mean? It means that if for a constant pressure, if a change in the volume happens, either an increase or a decrease, the work must be done on the gas. So if the gas compresses, then work must be done on it. If the gas expands, it means that the gas itself does work. And we state that when the gas itself does work, that work is positive. And we can prove it here since V final will be greater than V initial, so the work will be actually positive. But when the work is done on the gas, it compresses. So the final volume is less the initial volume, thus we get a negative value for work. Now let's move on to the second component. And just to make it clear, you should know that Q, of course, is the heat energy and is equals to mc delta T. You're supposed to know it from topic B.1. But now we're gonna go to the change in internal energy, which you probably know, but there's a very slight difference. So we know that, let's start. The internal energy of the object is given by two equations, 3 over 2 n r t, which is also equal to 3 over 2 n k b t. N is the number of moles, R is the ideal gas constant. These come together as a pair. So if you're using moles, you have to use the ideal gas constant, which is 8.31. And if you're using the number of particles slash molecules, you have to use Boltzmann's constant, which is 1.38 times 10 to the negative 23. And of course, number of particles, you probably won't be using this one because it gives you the number of moles, and you never have to use the number of particles except if they ask specifically for the number of particles of a certain gas. So what's the difference? Well, the change in internal energy, since we know that N and R, or N and K, B, are constants, they will never change. The only thing that can change is the temperature of the gas. So it's just going to be written like this, delta T, which is also equal to 3 over 2 N K B T. This means that if there's no change in temperature, then there's no change in internal energy of the gas. This also means that from the first law of thermodynamics, that the heat energy supplied is equal to work done. So if we do this here and set this equal to 0, so it's be Q equals 0 plus W. So Q equals W. Okay. Now I'll move on to a more complex topic in thermodynamics that you will not have encountered. It is one of the hardest and most students struggle with, although I haven't seen many questions on this, but I'll try to let you understand. So this is known as entropy. Let's just write the equation. What is entropy first? Entropy is a measure of disorder in the universe. And this is actually the second law of thermodynamics that states that the entropy of the universe is always increasing. So what is entropy? Well, I told you it's a measure of disorder. So by the second law of thermodynamics, that means that disorder will always increase in the universe. It will never decrease. If it decreases in one spot, it will increase by more in another spot, and the net change in entropy will be positive. So let's take, for example, a solid. I'll try to explain. A solid is made of particles stuck together, vibrate, and that's why they have low heat energy or kinetic energy, doesn't matter. But for a gas, they're farther away, they move. So we can say that gases have more disorder, have higher entropy than solids, since solids just merely vibrate a few millimeters, while gases can move wherever they want. So let's see. I'll try to explain it in terms of the equation. So it says that Q, the heat energy, divided by the temperature. So if I supply a solid with heat energy and keep on supplying it with heat energy, it will become more disordered, since its kinetic energy will rise and it will eventually become a liquid. Then it will, if I supply with even more heat, it will then become a gas, and it will be in a state of disorder, since it will be moving freely. And in the ideal gas model, we assume that gases, have no intermolecular forces between them, meaning that there's nothing actually binding the gases together. The only thing letting the gases together is the volume, or it's their container. If you leave the gases in free air, they could move very far away and move freely as they want. So there's nothing actually you can do about it. They're in complete disorder. And this is what the law states, that no matter what happens, disorder will always increase. let's assume I'll give you something to think about. A fridge. Inside the fridge, you could say that the entropy is decreasing, which is true because heat energy is removed. And from this equation, if heat energy decreases, then entropy must decrease. And this is, of course, occurs at a constant temperature for a fridge, probably. But what you don't know is at the back of the fridge, it releases all that heat. And all that heat makes the room in which the fridge sits in more hot, increases the heat energy of the room. And since we abide by the second law of thermodynamics, that increase in heat in the room is greater than the decrease, or the increase of entropy in the room is greater than the decrease in entropy in the fridge, and thus the net entropy decreases. And one more thing, the entropy, second law of thermodynamics only, or it applies to everything. But you must know that entropy could decrease if you're talking about a certain, like the fridge, for example, a certain microstate, we call it. But entropy can only decrease if work is done. And since in the fridge, work has to be done, there's a motor that powers, that takes the heat out. So work is done on the gas inside, and thus entropy can decrease. Another equation for entropy is this one. Yeah. So you see that you know that KB is a constant, so you might just ignore it. But what is then omega? So omega represents the number of microstates. What do you mean by a microstate, you can ask? A microstate is like something specific. So, for example, I would say that humans are microstates in the whole world. Each one of us is a microstate. We are all larger of a macrostate of all humans. So a microstate is basically a gas on its own, or many gas particles, sorry, on their own that uh, that we study. So the increase in number of microstates, of course, means that there's more energy, since there's more disorder, and thus S will also increase, of course. Now we move on to cyclic processes. So from the ideal gas topic B.3, where you talked about ideal gas laws, you know that there are three thermal processes, which are isothermal, isobaric, and isochloric or volumetric, but here I'm gonna write it volumetric. So what does this mean? Well, it's simple. When an isothermal process occurs, the delta T, the change in temperature, equals zero. Temperature remains constant. And you can also say this for isobaric. Baric, of course, is talking about pressure. So here the pressure is constant, or you can say delta T equals zero. And RZ volumetric will also be the same. But in this lesson, we add a fourth process, which is known as the adiabatic. So for the isothermal process, the change in internal energy is zero, since no change in no change in temperature. For the isobaric, necessarily nothing has to be zero. There can be heat energy added, there can be a change in internal energy, and there can be work done. And work will be done actually. But for isovolumetric, no work will be done. So, what controls heat energy? Since isobaric doesn't necessarily mean that Q equals zero, but isothermal means that delta U equals zero, and isovolumetric means W equals zero. So what process infers that Q equals zero? Well, this is the adiabatic process. This process is similar to isothermal, but the only difference is that no heat energy is supplied. So it's actually this process, in order to occur, it has to be done very fast. In order to because we don't want a change in the temperature. So there's actually an equation for adiabatic process that states that PV to the 5 over 3 is constant, meaning if you wanted to solve, for example, 5 over 3. If you wanted to solve for P, no, P remains constant actually. If you wanted to solve for initial P1 and V1 and you have P2, or you want to solve for V1 and you have P1, P2, V2, you would use this equation to solve it. So you would take the 5 over 3 root and rearrange. This is similar to the equation for ideal gas laws, which states that PV over T equals constant. But since here there isn't a change in temperature, we just exclude T since it's the same on both sides. But there is a factor of 5 over 3 that accounts for the adiabatic process. It's pretty different, but there's no actual explanation for why it's to the power of 5 over 3. And now on to the final part of thermodynamics. This is simple. I'll talk about it here. It's less about equations. The equations are pretty easy actually, but there is this cycle that is hypothesized, known as the Carnot cycle. So let's assume a normal car engine. For a normal car engine, it will never actually be able to work at 100% efficiency. Then there must be heat lost. It is impossible that no heat is lost. So there's actually another proposal that the maximum efficiency that anything can work at, any engine specifically can work at, is known as the Carnot efficiency. The Carnot efficiency, let's make that clear. Any engine works between two temperatures, which represent T cold and T hot, where, where T cold is the minimum temperature and T hot is the maximum temperature. So the Carnot efficiency is written like this. And Carnot equals 1 minus T cold over T hot. And the value you will get is absolutely theoretical. It is 100% theoretical. It is the maximum efficiency that a certain engine can reach. So 100% is actually not the maximum efficiency. The Carnot efficiency is the maximum efficiency of any engine that works between temperatures T cold and T hot. The Carnot efficiency is the maximum it could ever reach, and it is only theoretical because it assumes no heat loss or no losses to friction or other stuff. We use this to see how close maybe an engine is to its maximum efficiency. And you'll be asked in your exam, but it's pretty easy here. You'll be given, of course, the cold and hot temperatures, or you will be given other givens to find them, maybe. And the final equation here is equation you've took in topic 8.3 that states that the efficiency, normal efficiency here, is equal to the useful work divided by the input energy, which is simple. For example, for a car engine, the input energy would be the energy of the gas, of the fuel, and useful work would be the distance the car drove and the force at a certain speed. And this works also for power, and you would calculate the efficiency of the car engine. This is exactly the same actually for the one you saw in 8.3. So now let's solve a couple of questions on the topic so you don't forget. Let's see. Okay, question 1. This is a paper 1 question. A working refrigerator with a door open is placed in a sealed room. The entropy of the room: A is 0, B decreases, C remains unchanged, and D increases. Let's remember what I talked about. The second law of thermodynamics states that the entropy of a system is always increasing. correct? Unless work is done. But in here, this case, it's telling you a working refrigerator. He's not telling you the entropy of the refrigerator. He's actually telling you the entropy of the room it sits in. So since we're talking about the entropy of the room, it follows the second law since no work is done on the room actually. So entropy must increase in the room, and that would be D. Okay, another question. Which of the following processes can be represented as a vertical line on a PV diagram for an ideal gas? Okay, so a PV diagram is a diagram such as this, where P is on the y-axis and V. So remember the four thermal processes I talked about. One of them can be represented by a thermal line. Which one is it? Well, what does a thermal line, what a vertical line look like? Well, this is a vertical line where pressure is increasing and volume remains constant. So which process is when volume remains constant? Well, it is the isovolumetric process, of course. But in this question, it is also called the isochoric process. So you need to remember both names because in paper one questions, they won't actually give you both. So it would be an isochoric process. Let's move on to, okay, this is a hard one. Which statement is a consequence of the second law of thermodynamics in terms of statistical mechanics? Okay. Energy is conserved in all interactions. Well, that would be wrong. That is a consequence of the first law. B. The number of accessible microstates always decreases in an isolated system. Well, that's wrong because you know that the entropy is always increasing in the universe. That means that the number of microstates must always increase. So C. Entropy increases because system evolved towards macrostates with the highest probability. Let's save that and let's move on to D. The work done by an engine can be completely converted into heat. Well, if you see, we already eliminated A and B, and D is incorrect. We just stated that no engine can have maximum efficiency. So C would have to be the right answer by elimination, and your understanding, of course, of entropy. This question is easy. Let's move on to. I'm looking for an easy question here. Okay. Which of the following is the correct statement of the second law of thermodynamics? A. Energy cannot be created or destroyed. Well, again, this is exact statement of the first law, so it's wrong. B. Work is the product of pressure and volume. Well, this is not really a law. It's kind of related to the first law, so it's incorrect. Heat cannot spontaneously flow from colder to a hotter body. Let's keep hold of that. And the total momentum of system is conserved. So we know A and B is wrong, and D is of course wrong. The second law of thermodynamics has nothing to do with momentum. And yes, since we stated that the change in entropy is always increasing, this also means that heat cannot flow from hot to cold. It has to flow. Sorry, it cannot flow from cold to hot. It has to flow from hot to cold in a spontaneous manner. Of course, when work is done, that is possible. So that relates, of course, to the second law of thermodynamics. Okay, this is about second law of thermodynamics. Three statements about entropy are: number one, the entropy of a non-isolated system can locally decrease. Okay. Two, the change in the entropy of a system during a process is directly proportional to the temperature at which a process is carried out. Well, that's incorrect, of course. You can look at the data booklet, they're inversely proportional, actually. Three, the entropy of gas molecules in a sealed container is proportional to the number of possible microstates of the molecule. Well, that is correct, since we see the first law of the entropy equation, where it is directly proportional to the number of microstates. So, 1 and 3 are correct. Let's go on to the next question. Okay. Which process necessarily involves an increase in the total entropy of the universe? A. Isothermal expansion of an ideal gas. B. Adiabatic compression of an ideal gas. C. Melting of ice at 0 degrees Celsius in air at room temperature. D. Carnot cycle running in reverse between two reservoirs. Well, the only answer here would actually be B, since isothermal expansion of on an ideal gas means that there is an increase in temperature. And we know that the entropy is inversely proportional to the temperature, so entropy will decrease. Adiabatic compression means that no heat is supplied, since the change in heat is zero, the change in entropy is also zero. And Carnot cycle running in reverse actually is will decrease the entropy actually, because work is done to reverse a cycle, and reverse cycles actually always decrease entropy. So the only answer left would be C, which is melting of ice at 0 degrees Celsius in air at room temperature. In order for the ice to melt, heat heat must be supplied, and this means that increases and the entropy must increase at a constant temperature, and he even states that temperature remains at 0 degrees Celsius. Okay, this actually has to do with topic B.1, but we'll solve it. It states a liquid with mass flow rate m per second. So let's write flow rate equals m over t, and specific heat capacity C through a heater supplying power P. What is the temperature increase? Okay, let's write the equation that comes up to mind as soon as I write this is this equation, Q equals mc delta T. But we don't have Q and we don't have M, we only have C. So we have to think, power, this is energy, right? This is energy, this is heat energy. And it's saying that it's a heater, but that won't even matter. Heater supplies heat, so power is the rate of heat energy per unit time, so it's Q over T. So what we can do is divide both sides by T, and we get that power, since we know it's Q over T, equals mc delta T over T. And we have M over T, we have C, now we solve for T. So P equals M over T C delta T. Let's send the M to the other side. Oh, sorry, I made a very big mistake here. So it's actually saying that the rate of flow of mass is M itself. So actually, we would leave it as M, and it will be P equals MC delta T, but M is the rate of flow of mass, not mass itself. But M and Q equals MC delta T is mass. So don't get it confused. He's trying to confuse you here in the question. So since we have it rearranged, so it's gonna be P over MC equals delta T, which is correct. Okay, which of the following correctly expresses the first law of thermodynamics? Q equals MC delta T, U equals 3 over 2 nRT, PV equals nRT, or Q equals delta U plus W. Well, this is very simple. It's written in your data booklet, so it's C, of course. Third one I said. Which of the following processes is considered reversible in an ideal Carnot cycle? Okay. Rapid adiabatic expansion, isothermal compression with friction, quasi-static isothermal expansion, sudden adiabatic compression. So I'd actually say that it is rapid. Oh wow, I didn't know. Okay, a monatomic ideal gas contracts adiabatically from a volume V to volume V over 2. What is the new pressure of the gas? So let's use the equation that I stated, which states that P1 V1 to the 5 over 3 equals P2 V2 to the 5 over 3. So here we have three of them. We have P1 and we have V1, which is to the 5 over 3 equals P times V over 2 to the 5 over 3. We're solving for uh, P2 actually. So let's send it to the other side. It's gonna be P1 V1 over V over 2 to the 5 over 3. And this is of course to the 5 over 3 equals P2. Okay, now we have to simplify. Let's find the way here. P2 equals, let's actually reverse this and write it as it was. So what is V2 to the 5 over 3? Well, it's V to the 5 over 3 divided by 2 to the 5 over 3. You can use your calculator. You have it in both exams actually, so don't need to worry about that. We're just gonna write it 2 to the 5 over 3 because it's in decimals. And send it to the other side. And I can now cancel both these, correct? So P2 equals P1 times 2 to the 5 over 3, which can be written as P1 times root or cubic root of 2 to the 5th, which is one of the answers here. Let's solve the final question. Let's go. Let's find one here. Okay, this is an easy one. Which of the following distinguishes an adiabatic process from an isothermal process in terms of internal energy? Well, let's say delta U equals 0 for adiabatic, delta U is not equal to 0 for isothermal. Well, that's of course incorrect. So we know that isothermal, the change in internal energy is directly proportional to the change in temperature. So if no temperature in isothermal processes, delta U must equal to 0. So B, delta U is not equal to 0 for both, also incorrect. Based on the first assumption we made, delta U equals 0 for isothermal and delta U is not equal to 0 for adiabatic. So this would be the correct one, of course, since that all other answers actually state that delta U is 0 for isothermal, which is incorrect. By the equation, we can see that that is not true. If delta T is equal to 0, then delta U is equal to 0. Actually, I'll even solve another question. Okay, this is a more mathematical question. It's an easy one. So a 700 watt electric heater, so let's write your givens, P equals 700, is used to heat 1 kilogram of water. So M equals 1 without energy losses. The specific heat capacity of water, so C equals 4.2. What is the time taken to heat water from 25 to 95 degrees Celsius? So delta T, we can write it 95 minus 25, which equals 70. Now, I want you to remember one of the questions we solved, that we know that the power equals mc delta T over time. So if you rearrange for it, let's write it here, mc delta T over T. We have all the others. So just rearrange T equals mc delta T over P, which is equal to 1 times 4.2 times 70 divided by 700. Use your calculators, you'll find that it is equal to 21 over 5, which is 0.4. Oh, here's something we found that is wrong. So actually, C is not equal to 4.2. It is equal to 4 to the 2 times 10 to the 3 for water, which is written in kilojoules, and I did not see it, so we can just add 10 to the 3 here. The answer would be 420 seconds. So if you don't see 420 seconds in the answers, you change it to minutes to try to see if it's equal to one of the answers. So to change 420 to minutes, you divide by 60, which will give you 7 minutes, which is one of the answer. I'm sorry, but let's just solve the final question. So it states, which of the following correctly describes entropy? A measure of the internal energy of the gas. Of course, this is wrong, completely wrong. A measure of disorder or randomness in a system. And if you know entropy, and if you focused in this video, you'd know that is the correct answer. This is the exact definition of entropy. It is a measure of disorder or randomness in a system. So it would be B. I'm just gonna solve a final question here because I saw a question that I like here, and I wanted to solve many paper one questions, in many different ways. So we solved on everything. So it states a 4 kilojoules of heat. So it's saying that Q equals 4,000. I like to write it in SI units as soon as I can so I don't get confused at the end. It's supplied to a Carnot engine that operates between 350 and 400. So 350 and 400. We know that one of them is T hot and one of them is T cold. So of course T cold would be the lower one, which is 350. And T hot equals 400. The engine applies a force to a block to move it 2 meters. So there's displacement of 2 meters. Let's write that down. And in the direction of the force. What is the average force applied to the block? Very nice question here. First, he's talking about the engine here, correct? So in order to find how much work has actually been converted to force or how much heat energy has been converted to work, we have to see the Carnot efficiency of the engine because here it states it's a Carnot engine, so it is theoretical but it is working at maximum efficiency. So you know that Carnot efficiency equals 350 divided by 400. Oh, sorry, 1 minus 350 over 400, just T cold over T hot. This is gonna be equal to equals 1 over 8 on your calculator, which is equal to 0.125 or 12.5%. So now you have the efficiency. Now you can calculate the percentage of that heat energy that has been converted to work. So 4,000 times 1 over 8, let's write it as fraction, will be equal to, using your calculator again, 500 joules. Correct. So we now have the work done. We know that work equals Fs from topic 8.3. You have S, you have work, 500 divided by 2 equals 250. So the answer is 250 newtons. So today we reviewed topic B.4, thermodynamics. We solved a couple of questions. I think you have to just practice on this topic really. It's not one of the major topics, but I won't tell you not to study it because in my exam, May 2025, it came up as an 8-point question, and you don't want to lose 8 points on nothing. And it came up several times in paper one actually. So it made about 12 points in the whole of exam, which is a lot for a very small topic. So I advise you to solve as much as possible past paper questions. And if you don't understand anything, you can write in the comments or you can go to the book. I think if you solve exercises in the book first before moving on to past paper questions, you'll find it easier because you're gradually solving harder things. But I advise you to focus on this topic. It is one of the most important topics, and I think it actually helps with understanding the rest of topic B, excluding B.5. So it helps with understanding the rest of topic B, and I think most topic B questions actually are also accompanied by this for HL students. So I would advise you to study, and thank you.